All right, everyone, welcome to another office hours video where we're going to do a little bit of practice with our graphical vector addition and subtraction. If you're not sure what I mean by graphical addition and subtraction of vectors, you can head over to the MathBytes video that's linked in the description about what vectors are and how we can add and subtract them together. This is going to be a really important skill in physics because we're going to be working a lot with vectors. And so being able to quickly kind of like understand or have some intuition for what combining vectors is like and like what combined vectors look like is going to be really helpful when you're sanity checking physics problems later on. Okay, so what I've done here is drawn three vectors, A, B, and C in different colors. And we're just going to do a couple problems working with how to add and subtract these together. And I've just written three of them. And they involve some mixture of like vector addition, subtraction, and some scalar multiplication. And so we'll see kind of all the skills we talked about at use from our MathBytes video. Okay, great. So this first problem is just going to be a straightforward sum of all three vectors. And so I've defined this vector u to be the kind of resultant vector, and we want to find out what the vector u looks like after we've done all the operations on the right-hand side of this equation. All right, so remember, it doesn't actually matter what order I do this operation in. I can start with b and add a and c to it. I can start with c and add b and a. Like, it doesn't matter because vector addition is what's called commutative, right? Like we talked about in the MathBytes video. But just because they're in order A, B, and C, let's do them as is. So remember, with vector addition, we can always start with the first vector as is. And so all I need to do to begin is just draw my first vector A, or some approximation of what A might look like. It's not exact, but it's about right just to give you a flavor, right? And if I want to add another vector to this, remember the rules for vector addition are I just take my vector B and I kind of place it so that the beginning of B starts at the end of A. So I lay them kind of end to end, right? And so what that means is B is kind of the shallow downwards to the right pointing vector. So let's kind of append it here. And this is what vector B might look like. And so like I said in the MathBytes video, we can just keep tacking on vectors, right? We can add more than just two vectors together. And so now that I know where the end of B is, that's what lets me kind of think about putting C at the end of B in order to make sure I can add the C vector right at the end of this, right? So just like I put B at the end of A, I'm going to take this C vector and imagine sliding it kind of over to the end of B. And so now C looks something like that. And so now what I've done is constructed the vector sum graphically. And the total resultant vector is just going to be the vector that points from where I started, which is right here, this initial point where we started drawing A, right? And I'm just going to follow these arrows and see where the final endpoint is of all these instructions. And remember, the resultant vector is just the vector that points in a straight line from this purple initial spot to that purple end position. And so this vector in purple is going to be our resultant for the first problem, right? And you'll find out, if you have a pen and paper, I recommend kind of drawing three approximate vectors. And just to show that vector addition is commutative, try putting them in different orders, right? So we could try doing like B first and then add A and then C. And the idea is that we should be able to show that no matter what order we do this in, we should get the same final resultant vector. Okay, so hopefully that was a nice straightforward problem. We didn't have to do any scalar multiplication or subtraction. So this one's just kind of like thinking about copy pasting all these vectors on top of each other. The next problem is going to include a little bit of scalar multiplication. And so remember, when we're doing scalar multiplication with vectors, just like how we have this 2 in front of this A, right, we're multiplying vector A by a scalar. And the effect of that is to take the same vector and it's repeated addition, right? So if I have two A's, then what I'm going to do is think about having my first A like this, and I have a second one, so I need to lay the second one right on the end of the first one, so that we have our two A's put together. And this kind of entire red vector represents what 2A looks like. Notice, just like we talked about in the MathBytes video, it has the same direction because it's the same vector kind of put on top of itself, right? So we're never going to be able to have any vectors that aren't exactly like parallel, right, if I just multiply by a scalar. But the thing is, because we have two of them now, it's going to be twice as long, right? So the important thing to remember here is that scalar multiplication has the effect of increasing the length of a vector, but it doesn't change the position at all. And so now I'm actually going to slide this down just a little bit to the left so we have some more room to work with. But now we see that the second part of this sum is going to be vector b, right? So I can think about, once again, taking my vector b and just copy pasting it on the end of this second vector a. so that I can lay them, I can sort of start B where I ended A, right? That's how we do our vector addition stuff. So what I can do is start here, and I draw my kind of approximate copy of vector B. And because this is all the sums, then I know that my initial, my vector initial kind of starting point, my resultant vector U, is going to start from where we started this first A. And if I follow these arrows, right, the final position that we're thinking about is this purple dot here at the end of B. And then the vector U, which is 2A plus B, is just the vector that points from this purple dot to this purple dot. And now this is what it looks like when we have some kind of scalar multiplication mixed in with our usual vector addition stuff. And so finally, our last problem is going to involve a little bit of scalar multiplication and a subtraction problem, just so we can see kind of what this looks like in practice. And so, like I said before, right, we want to take a look at this first thing and break it down. We see this first vector is 2 times b. So what I want to do is draw a vector that looks like b, but because there's a scalar multiplication of 2 in front of it, I need it to be twice as long, right? So what I'm going to do is take my vector b, and I'm just going to draw kind of an extended version. It'll be approximately twice as long, right? If you're doing this in class, by the way, you might be doing this with like very precise like rulers and angles and stuff. But what we're doing here is just kind of like approximate, so we can see the method. And then at the end, you know, if you wanted to, you could like measure the distances and the direction of your final vector if your professor or teacher asks for that kind of thing. But this way, we have 2b. Which is our first vector, right? And the second vector we have is minus 3c. So remember, when we do subtraction with vectors, one thing that's good to remember is that really this isn't a subtraction problem. We can rewrite this as an addition problem, where we have u equals 2b plus, and then remember that subtraction is really the same thing as adding the negative, right? So now we can remember that our c vector initially pointed, I'll draw that a little better, in a direction like this, right? This is kind of approximately what our c vector looked like. But because we need the opposite of it in order to subtract it, we can think about drawing this negative c vector that goes in this direction. The negative sign has the effect of flipping the vector's direction, but preserving the length, right? And I see now I've not given myself enough room for this, so let's take this whole array and slide it up a little bit. And so there's this green vector that we've drawn here is just what a single negative c looks like, right? And if I tack 2 more onto those, then we can construct our full negative 3c. And this way, we can see that the whole minus 3c vector is really just the c vector flipped over, and the scalar, once again, has the effect of taking the length and multiplying it by 3, right? So now that I'm looking at this, it's definitely not quite to scale, but that's okay. The important thing is we just kind of get a good feel for how the subtraction actually works, right? So we started with 2b, which is a vector parallel to b, but twice as long. We tacked on by adding a negative 3c vector, which is the opposite direction as our original c vector, right? That's what the minus sign does, and it's 3 times as long. And if we follow these instructions, then we can see, let me draw that in purple, that the initial position is up here at the beginning of 2b, and the final position is kind of here in the bottom right corner of our page. And so we know that the resultant vector from here is from this initial purple dot all the way down to this final purple dot, like so. And so in this way, these are some kind of simple problems with vector addition and subtraction. You won't run into too many of these later on when you're doing physics, but it's really important to be able to like kind of sketch these out sometimes if you're trying to sanity check a problem, right? And so I'll call it there for now. I think vector addition and subtraction is pretty straightforward once you get a good feel for it, and hopefully these 3 example problems have given you a good idea of what this looks like. There's also plenty of practice worksheets online that you can find. If you have trouble finding any, you can just hit me up in the comment section or via email, and I'm happy to like send you some or point you to some resources or something like that. But that's really all the problems I have. This is a nice short and sweet office hours video. As per usual, if you have any questions or thoughts you want to share, please put those in the comment section below, and I'll be happy to address those. If you want a refresher on vector addition and subtraction, once again, please head over to the MathBytes videos, where you can see kind of the introduction to this content. And that's really all I have. In the next video on vector addition and subtraction, we'll be working with some like vectors and adding them algebraically instead, and seeing kind of how the graphical vector addition and subtraction line up with the way that we do them in physics when we're actually like trying to find the full exact results numerically. All right, as per usual, please don't forget to like and subscribe for more free physics problem solving tips. This has been Physics Tutoring Quantized.